Hello maths fans, I'm Dr. Tom Crawford, a mathematician at the University of Oxford and the University of Cambridge, and today I'm going to be taking the New Zealand Scholarship Calculus exam with zero preparation. As usual with this type of video, I know nothing about the exam I am about to sit, other than it is obviously mathematics. Specifically here, I'm expecting something to do with calculus, given the title is Scholarship Calculus. I know it's come from New Zealand, and I also know that it is taken by high school students between the ages of 16 and 18. I have 3 hours, which is pretty long, to answer 4 questions for a total mark out of 32, which seems to suggest these are going to be quite difficult, in-depth questions. Right, I think that's enough stalling. Let's see how it goes. New Zealand Qualifications Authority, Scholarship 2023 Calculus question booklet. All right. Before I forget, as usual, I will put a link to the exam paper and the mark scheme in the video description, so you can have a go at this along with me, and you can also check my answers at the end, but I will also do a quick marking as I usually do. Question 1. Let's get stuck into it. The graph below shows a circle and a hyperbola. Let's start by drawing this diagram. So we have a circle, like so, and then hyperbola, fun, coming through. So let's just kind of emphasize that a little bit. We've got these points P, Q, and we've got R, which is going to be over here, T, which is going to be down here. Okay. And we've got an unknown radius for the circle. So x squared plus y squared is going to be r squared. And then we've been told hyperbola is xy equals k, where k is positive. Right. So P has coordinates -8, 6. Okay. So we want to work out QR. So if P is at -8, 6, then by the circle equation, we can actually use that to try and work out the radius, because that's going to give me a location of R. So has to satisfy the circle equation because P is on the circle. So therefore 64 plus 36 is equal to R squared, which is 100. So R is 10. So we now know that the position of capital R is going to be at 10, 0. Right. Now I need the point Q. So P and Q are both on the hyperbola. So by the hyperbola equation, what can I work out? I need -8 times 6 must equal k. But k is positive. Is k positive? Oh, I don't know that k is positive. Okay, so I don't know why I wrote that. Do not know that, because I was going to say it doesn't work because k is actually -48. So k is -48. And then Q is also on that line. So I need xy equals -48. And also on the circle. So it's just swapping them, isn't it? So I think I could sort of make this more formal, but I think you can kind of see where I'm going here. So it's just going to be x is going to be -6 and y is going to be 8. Right? So judging by the picture, we're a little bit more, we're not as far out. So we're slightly less negative for x and higher for q. So that's going to be -6, 8. And that still satisfies the circle equation and still satisfies the hyperbola equation. Okay, so that's going to be the location of q. So now I just need the straight line. So the line QR joins -6, 8 to the location of R, which is 10, 0. So equation of a line, what is it? Y minus y1 equals the gradient times x minus x1. So that's y minus, I don't know the gradient, do I? There's a way of doing this with y1s and y2s as well, isn't there? All right, maybe I can work out the gradient. Let's just do it that way. So what do I know? I'm going from -6, so I'm going 16. Oh, okay, so x moves 16 whilst y moves 8. So the gradient, so it's y equals, God. We've got a negative gradient. Yeah, we very much, let's draw this line on. We've got a QR, which is going to be a nice negative. Okay, so this is negative gradient. And for every, and what I'm sort of saying here is we have 16 there and 8 there. So the change in y is 8, so it's over 2. So y is equal to x over 2 plus c, I think, he says. And we also know that r is on there, and r is at 10, 0. So that means that 0 must be 5 plus c. So c is -5. So I think the answer to the equation of the line OR. So I think the OR has equation y equals x over 2 minus 5. And I'm just going to double check that, not OR, QR. I'm going to double check that that makes sense now, because I need -6. So let's just check the point Q. So when x is -6, we get y should be 8. So 8 is equal to -6 over 2 minus 5. Yes, that works. So the point lies on the line. That's the equation right there in that box. Okay, part 2. Moving on swiftly. Let's see. Do not want to spend all 3 hours on this paper. We'll see. Okay, so that's part 1. Part 2, prove that the line RT is parallel to the line PQ no matter where the hyperbola intersects with the circle. Okay, so we want to show that RT is parallel to the line PQ no matter where the hyperbola is intersecting. Right, so I'm going to draw another picture here just to kind of focus on what's happening. So we've got a circle, we've got a hyperbola, we've got a line here between these 2 points, and then we're also saying there's, so this is P and Q, and then R and T down here, and then we're saying that these two are parallel, question mark. Okay, so diagram suggests they are, but I'm going to need to do a bit more than that. I can't do a proof by diagram, can I? So let's think about this. So what do I know about R and T? So R and T is 10, 0, and 0 minus 10. So that line is it y equals x? Let's see. So RT, so I think that line is going to be y equals x minus 10, right? Because it goes through, when x is 0, y is minus 10. When x is 10, y is 0. Okay, so the line there is y equals x minus 10. So I need to think about PQ and what the gradient of that line will be. So I need to, so my question here is, what is the gradient? So that has gradient 1, RT. So what is the gradient of the line PQ? Because if I can argue that the gradient of that is also 1, then they're parallel. Right, but why would that always be true? That's a good question. So let's think about this. Could I try and find so I'm thinking here maybe I could try and calculate the gradient, because Would that work? So what do I know? I know that y is equal to minus 48 over x. So that's the hyperbola. So I can say that dy by dx, which would give me the gradient of the hyperbola, is going to be 48 over x squared. So differentiating that. But what do I know? But then I'm looking for the points. But I want the 2 points of intersection. No matter where the hyperbola intersects with the circle. So I wonder whether you can just argue via symmetry. So I'm thinking here, I'm like, can we calculate this? But given, I think the question's suggesting like we could change the value of k, or we could change the radius of the circle. I think it's trying to argue that you could do that and still get this kind of same answer in a way. So I don't think I'm supposed to use the exact points, having reread the question. So I think you can just argue from symmetry, because the line RT, right, so they both basically, both of them, if I draw this in blue, you can say they are both normal to the line y equals minus x by symmetry. So if they both have the same normal, right, so that means they're at right angles here. If they both have the same normal, then they must have the same gradient, and therefore they must be parallel. That's the idea. So I think that is going to give me the answer. He says with little confidence. It feels like it should be true. So if I were to like draw another hyperbola, for example, you're going to have a similar kind of behavior up here, but you're still going to get this symmetry. So no matter how you change the constant, the k, for your hyperbola, you're always going to have this line of symmetry through y equals minus x. And the same with the circle. The circle's always going to have that symmetry as well, and therefore the reflection of r and t, even if you increase the radius, they're always going to have that symmetry line through the straight line joining r and t. So I think that's valid, but I don't know. But in the interest of time, I said I don't want to spend 3 hours, so we'll move on. But I think that's kind of the idea. There's a symmetry argument that can be made there. All right, so something completely different, nothing to do with circles and hyperbolas. We've got to solve a system of logs. Bloody hate logs. Anyway, right, well, let's just get to it, eh? 4 log base 2 of 8x cubed plus log base 5 of y to the 6 equals 17. And log base 2 of x to the 5, log base 2 of x to the 5, right, plus log base 5 of y squared plus log base 5 of y squared equals 3. Okay, so this is just rules of logs. I'm assuming try and simplify for like whatever log of x is and then figure it out from there, I think. That's my plan. So let's start with equation 1 and equation 2. So from equation 1, we can say, using some rules of logs, this is 4 log 2 of 8 plus 4 log 2 of x cubed, sure, plus now bringing the 6 down from the y to the 6, so plus 6 log base 5 of y equals 17. But then I can say log base 2 of 8 is 3, so that's 12, because 2 cubed gives me 8. So that's 12 plus, bring the 3 down from the x again, plus 12 log base 2 of x, plus 6 log base 5 of y is 17. So I'm just going to relabel that as 12 plus 12 capital X plus 6 capital Y is 17, where... because I don't want to try and like do inverse of logs, right? I don't want to take exponentials. So I want to say where capital X is log base 2 of X and capital Y is log base 5 of y. Because I can see the second equation is also going to be in terms of those variables. So I might as well work like that. Okay, so now the second equation. So log base 2 x to the 5. So that's now 5 log base 2 of x plus log base 5 of y squared, so plus 2 log 5 of y, and that has to equal 3. Right, so that's just 5 capital X plus 2 capital Y equals 3. So we now have two equations. So this is going to be one of them, which is nice and simplified. And then simplifying the earlier one, we can say 12 capital X plus 6 capital Y is equal to 17 minus the 12, so is equal to 5. Right, so we've got to solve these two simultaneously. Okay, so what am I going to do? I'm going to times the top one by 3, aren't I? So 15 capital X plus 6 capital Y is 9, and then I'm going to subtract them. So let's do that one minus that one, in fact. Keep it positive. So 3 capital X equals 4, so capital X is 4/3. So that means that log base 2 of x is 4/3. So x is 2 to the power of 4/3. Going to leave it at that. It's an answer. And then capital Y, subbing back in. So we get, what am I going to sub in here? Capital X is 4/3, let's say. So 12 lots of 4/3 plus 6 capital Y must be 5. So 12 times 4/3 is going to give me 16. 16 plus 6y is 5. 6y is, negatives. I think that's okay. We'll see. 6y is therefore minus 11. So y is minus 11 over 6, but y was log 5 of lowercase y is minus 11 sixths. So y is 5 to the power of minus 11 sixths, which is also known as 1 over 5 to the power of 11 sixths. So I think they're the answers. I have no idea. They look horrible, but I'm going to move on to part C. What are we doing now? I'm going to imagining something completely different based on this thing so far. Line L intersects. Oh, it's back to like part A then. Intersects the parabola y squared equals kx at points A and B, such that OA is perpendicular to OB as shown. Show that the line crosses the x-axis at K0. Geometry problem then. Okay, so I'm going to need a nice diagram, aren't I? So let's start with that. So it's like this. We have a parabola coming in like so. And then we have A just coming in and hitting the origin. And then going out and hitting another point over here. And that is a right angle. Okay, so nice right angle there between A and B. Okay, like so. Lovely. That's the line L. And then we have to show this intersection point. Right. So how are we going to do this? Okay. So let's think about the points where we are intersecting, shall we? Okay. So if okay. I'm going to start by making the point A a general point, and then see if I can do some algebra, because I have the equation for the parabola, and I also know about this perpendicular OA versus AB. So I'm hoping I can use something there about the product of the gradients being -1. That's kind of sort of the method taking shape in my head, but we'll see. So let's suppose let A equal A comma B, so lowercase. So what do we know then? We now know at that point, we know that B squared is equal to KA. So we now know the value of K, the sort of the term in our parabola. We now know what that is. So K is A over B squared. Right. Good. So that gives us something. We also know the line OA has gradient, so that's, just to sort of draw this on the diagram. So OA, if we go across here and up here, right, because we've labelled that point, we know that this is A across and B up, so we know that gradient is B over A. So this has gradient B over A, which implies, because it's perpendicular, OB has gradient minus A over B, because the product of the two gradients must be -1 because they're perpendicular. Now, since the line OB goes through the origin, we can actually work out its equation. So therefore, OB has equation, again, because it goes to 0, 0, y equals, it's going to be minus A over B times x. Now, we know that this then intersects the parabola at the point B. So intersects parabola at the point B. And what we want to work out are the coordinates of this point B. Right, so we've got the equation for the line OB. We know it's intersecting the parabola at B, and we know what that equation is. So we know that at B, parabola equation tells us that y squared is kx. So, how can we use this? Well, this one's going to tell us now that x is equal to minus b over a times y. So if we sub that in, that tells us that y squared, so at b, we can say y squared equals k times minus b over a y. So we know that y isn't 0 at this point, so we can cancel one of those y's and say y is minus kb over a. So now we know y, which is negative, which is good. That's what we expected. Then x at that point, it's still on the line OB. So x is equal to minus b over a times y, which is minus kb over a. So that's going to give us now pluses. It's going to be kb squared over a squared. So I think the coordinates at the point B are going to be xy equals kb squared over a squared, comma, minus kb over a. And at A, because we're going to use these 2 points now, we have 2 points. This is like part A. We have 2 points on a straight line, so we can deduce the equation, hopefully, and then get the intercept. We'll see. So at A, we know that xy is equal to AB. Right. Whew. So let's work out the gradient. So gradient of L. So that's equal to the change in y over the change in x between these 2 points. So we've got the point A. So we've got, let's kind of draw it over here, shall we? So we have something like this, and then we know this bit is B. We know oh God, what do we know about this? We know that one. We know the total distance is A. So this one is A minus kb squared over a squared along there, because we're subtracting from the point B. And then this one is kb over a. So I think the gradient is b plus kb over a divided by the change in x, which is a minus kb squared over a squared. So I think the equation, therefore, is, so equation of L is y equals this thing, which is a bit of a mess, but we'll just leave it as is for now, kb squared over a squared, times x plus c. We know this goes through, passes through AB, the point A, which is AB. So we know that B equals this gradient, we'll leave it as mx, not mx, ma plus c, like so. So c is equal to b minus ma. So I think the final equation is y, so this is for L, y is equal to mx plus b minus, so it's m times x minus a, isn't it? Right, so that's going to be this thing, kb over a over, this thing is a mess. I hope this works. I really hope this works. That times x minus a plus b. Okay, so I think that's the equation of L, hopefully. So now, what have we actually got to work out? Crosses the x-axis at k0. So, when y equals 0, what is the x value? What is x? So if we set y as 0 and try and find x, hopefully, fingers crossed, it will come out as k. If I've done it correctly, which is a big if. But they are just going to be horrible, so let's get stuck in. Right, so if y is 0, what is x? So I think we've got 0 equals mx minus ma plus b. So that tells me that mx equals ma minus b, taking those across. Then dividing by m, I can say x is now a minus b over m. Right, and I know what m is, and I'm going to do the inverse of that. So I think x should be a minus b times 1 over m. 1 over m is a minus k b squared over a squared divided by, we've got a factor of b there, haven't we? Nice, 1 plus k over a. Right, so I factored that b out because now I can cancel that, and that will hopefully help a little bit. And then we're going to put this over a common denominator. So it's going to be a plus k, yep, minus a minus k b squared over a squared, all divided by 1 plus k over a. Okay, so that one's going to disappear there, the a and the a, and we're going to end up with, and it's going to be a plus, nice. So that's going to be k plus, oh, it's going to be a times a 1 plus b squared over a squared over, and this is x is equal to 1 plus k over a. But, and this is fingers crossed, I think I know what k is from earlier, because k earlier I said was a over b squared, where k, oh, I need k to be b squared over a. Question mark. Was that not what I found though? It is what I found, I'm just an idiot. So k is not a over b squared, you tit. Good work, Tom. So I made a mistake, but I spotted it. K from this equation is b squared over a. K is b squared over a. Now I don't think I actually used that at any point from that point onwards, but nonetheless, because it seems to have worked, because now I can sub in, yes, that is correct. K is b squared over a, and so x is indeed k, which is the intersect. All right, cool. So that I think is what I had to do. That's the end of question 1. I am not going to bother checking any more working. I'm going to move on to question 2. Question 2 is starting with some trig. Then we've got complex numbers, more complex numbers, circles. Okay, this looks more up my street. Didn't really enjoy the geometry of question 1, if you couldn't tell. Didn't really feel like calculus. Scholarship calculus. Anyway, so let's get on with question 2. Stop stalling. All right, given the following, so we know that 3 pi over 2 is smaller than x is less than 2 pi. Right, so we're in the third quadrant. And we also know that cot of x, which I'm going to rewrite in a helpful form, which is cos of x over sine of x. So we know that is minus 5/12. Hang on a minute. That's a triangle, isn't it? Because that means that tan of x is minus 12 over 5. But then let's think about this. So that's going to be in the third quadrant. We're going to be down here then, aren't we? So this is x, and tan of x is opposite over adjacent. So that's opposite minus 12 over adjacent 5. Yes, and that would fit being in the third quadrant if this was like the axes here. Okay, right, so that's 13, isn't it? It's one of those classic, it's not, I was about to say it's a 3-4-5 triangle. It's clearly not the 3-4-5 triangle. But it's the Pythagorean triple. That's the phrase. It's a Pythagorean triple. You've got 12 is 144 plus 25 gives you 169. So the diagonal's 13. Okay, right. Thank you, brain. That was a good spot. I think, don't know if it's going to help, find the exact value for sine of x over 2. Okay, interesting. So I know sine of x because I know the triangle, right? So sine of x, just from the triangle, is opposite over hypotenuse, is minus 12 over 13. Yep. So that's sine of x, but we want sine of x over 2. So that's half angle formula. Oh God. Ugh. Sine of x over 2. Let me think about this. So I know that cos of 2x is, I have to think about this. Cos of 2x is cos squared x minus sine squared x, which is then 2 cos squared x minus 1. Yes. So that's not helpful. But I know that sine of 2x is 2 sine x cos x. Okay, perfect. So therefore, sine of x is 2 sine of x over 2 cos of x over 2. Right, yes. And I know that, I want that one, so the only one I don't know there is cos of x over 2, but I can get that from here, because I can say cos of x, which I know, is 2 cos squared x over 2 minus 1. So cos squared x over 2 is just 1 plus cos x all divided by 2. Yes. Cool. Right, okay. I think I've got a plan of attack here. So I'm just playing around here with double angle, half angle formulas. So I have a formula for sine of x over 2 in terms of sine of x and cos of x over 2. I know sine of x, and now I can get cos of x over 2 in terms of cos x, which I know, so I can kind of put all the pieces together. So, right, so let's work out cos of x over 2. So cos squared of x over 2 is equal to a half of 1 plus cos x. Cos x I know from the triangle. So cosine of x here is staccato, pairing. So adjacent over, so it's 5/13. Okay, so this is a half times 1 plus 5/13. So times 18/13. So that's cos squared of x over 2. So cos of x over 2, so that's obviously 18/26. So cos of x over 2. I don't know if I want positive or negative though, do I? Oh, okay, well let's just see what we're doing. So cos of x over 2 is plus or minus square root of 18/26. Sure, fine. What range are we in? Let's think about that. So I draw the graph of cosine to look like that. And we were told that x is between 3 pi over 2 and 2 pi. Okay, so we're between here. So we're between 3 pi over 2, 2 pi, right? That's for x. So x over 2 is between 3 pi over 4 and pi. So that's here and here. So it's the negative one. So cosine is negative, right? So you can say this is negative, right? So now we have all the pieces. We can use the equation star and say that sine of x, which we worked out was minus 12/13. So minus 12/13 equals the thing I want, 2 lots of sine x over 2, and then multiplied by cosine, which we just worked out was the negative root 18/26. So rearranging this will give us sine of x over 2. It's going to be positive, which is correct because x is between 3/4 pi and pi, and sine is positive on that range. Sorry, x over 2 is between that, so that works. So I think we're just going to simply get sine of x over 2 is therefore equal to, divide by the 2, you've got a 6/13, and then you've got a root 26 on top, 18 on the bottom. So we can simplify that a little bit. It's going to be a 6 times a root 2 and a root 13. And we've got a 13 on the bottom, we've got a root 2, and we've got a 3 from the root 9. So that's going to reduce, because of those two, you can get 2 over root 13, I think, is my answer for part A. So let's move on to B and complex numbers. Hopefully these will be a little more up my street, but we'll see. This has been pretty hard so far. I had to think. I definitely had to think. As one should when taking a maths exam. All right, z is equal to minus a half plus root 3 over 2 I. Find z bar to the 4th. Right, so z bar is the conjugate, which is minus a half minus root 3 over 2 I. So let's square it. Z bar squared is just minus a half minus root 3 over 2 times I times itself. Minus a half minus root 3 over 2 times I. Right, so let's expand that out. We're going to get a quarter plus root 3 over 4I plus another lot of root 3, so plus 2 lots of that. And then at the end plus, but then it becomes a minus 3 over 4. Because it would be a plus, but then the I squared gives you the minus. Marvelous. So I think z bar squared is minus a half plus root 3 over 2I. So therefore z bar to the 4th is that squared. So z bar to the 4th is therefore minus a half plus root 3 over 2I times minus a half plus root 3 over 2I. So we'll expand that and get plus 1/4 plus root 3 times root 3 gives us another 3 over plus 3/4 times I squared. So it's going to be a minus, which I'll do in a minute. And then minus root 3 over 4I, and then minus another lot of that. So I think it's a quarter minus 3/4 minus root 3 over 2I. So that's minus a half minus root 3 over 2I. Cool. Is that it? That would appear to be it. All right, let's move on to part C, shall we? Okay, Euler discovered an exponential equivalent polar form, blah, blah, blah. Yes, we know all of this. Euler's identity, yes, marvelous. Use this identity or otherwise. So we're going to use the identity, e to the I theta. Also, side note, they mention the notation z equals r cis, C-I-S, theta. Hate that notation. Fully, huge dislike for that notation. So bad New Zealand, bad New Zealand. But nonetheless, I don't need to use it because I know Euler's identity and it tells me to use Euler's identity. So that's what we're going to do. All right, determine the real value for I to the I squared. Right, fun one. So I to the I is equal to, okay, I have to think about this. So I is e to the I pi by 2. So that's e to the I pi by 2 to the power I. Something to the power and then taken brackets power you multiply. So that's just e to the minus pi by 2. So I to the I squared is just e to the minus pi by 2 squared. And again, we multiply that. So that's just e to the minus pi. What a nice result. I to the I squared is e to the minus pi. Assuming it's correct. Okay, is that it? That is it for C part 1. Okay, so that's part 1. C part 2. These questions are more like it. Right, the complex number, oh god, log, okay, so we're doing natural log of minus 25 EII, Christ, minus 25 EI to the I. Is that right? I to the I, it is. In exact rectangular, I don't know what rectangular form is, but I think it means A plus BI. All right, fun one. So what is that? That is equal to natural log of, So I want to split them up, but I don't think I can. No. Fine. So what's e? E to the II. I need to work out what that is, don't I? Okay, so I to the I is e to the minus pi by 2. So this is e to the, so this is exponential of e to the minus pi by 2. Okay, fine. Now, so that is log, so in a way, this is like log AB, isn't it? So this is, let's make sense of this. So I think I can use the fact that log of AB is log A plus log B. So I think what we've got here, so using this, I think I can say this is equal to log of minus 25, and I'll worry about the negative in a moment, plus log of the exponential of e to the minus pi by 2. But of course, the log and the exponential cancel out. So I think this is the log of minus 25 plus e to the minus pi by 2. Now, can I simplify log of minus 25? Does that make sense? So I'm struggling a little bit because you normally don't define logarithms for negative numbers. Now, I could try and define the complex logarithm, but I don't know if that's what they want me to do. But if I were to do that, again, don't think this is what I'm supposed to do, then you define the complex log or log of z is equal to log of the modulus of it plus I times its argument. And because we're minus 25, the argument would be pi. So I think it's log 25 plus I pi. That's how I would make sense of it using complex analysis, which I definitely don't think I'm supposed to do here. but maybe I can factor out the -1. So can I say, I don't know if this is allowed, but can I say that this is log of -1 plus log of 25 plus e to the minus pi by 2? Because now we can use Euler's identity, because this is then log of e to the I pi. Because e to the I pi plus 1 is 0, is the way I would write Euler's identity, but e to the I pi is -1. And then I can cancel it, and then, and then I'm gonna get the complex log back. Okay, great. So I could have just used complex logarithms, which is definitely, again, I think a little bit advanced for this, but I think it's give you the answer, because I'm going to get log 25, which now makes sense, right? That is a very well-defined function. E to the minus pi by 2 makes sense. So I think the final answer then, cancelling those two, is I pi plus log 25 plus e to the minus pi by 2. And all of those are well-defined, and that is in an a plus ib form. So yeah, let's do that and move on to part D. General equation of a circle, yeah, looks like this. I agree. Ax squared plus y squared plus bx plus cy plus d is 0. Sure. If z equals x plus iy, okay, z is x plus iy. Yep. So any circle can be written in this other form. All right. So sub it in. In short, so z times z bar is x squared plus y squared. That one's easy. Yep. How do I get x? Well, that's just z plus z bar over 2. Gives me the real part of z, which is x. And then if you do z minus z bar, I think over 2i, that will give me y. Right. Because z, so let's just check, z bar therefore is x minus iy. So z minus z bar, lose the x's, get 2iy, divide by 2i. Great. So I think then this is now just going to be a times z bar, yep, plus b times x, which is z plus z bar over 2, plus c times y, c times z minus z bar over 2i, plus d is 0. Right, and what did I have to get it in the form? So alpha form that they want has this is therefore alpha. How many z's have we got? We've got b over 2 plus c over 2i lots of z. Right, so I've got that one and that one. And then z bars, I've got a b over 2 minus, not plus, minus minus c over 2i times z bar. And then plus d, so d is gamma. So d is just gamma. Okay, so I think then we've got alpha is a, right, I should state this. So alpha is a, gamma is d, nice and easy, and then beta and beta bar. So I think beta is b over 2, and then rationalizing the denominator, multiply top and bottom by I, minus c over 2 times I. And then the other coefficient, so that means that beta bar should be b over 2 plus c over 2i. And this is actually equal to b over 2 plus c over 2i, lots of z bar. Yeah, so that matches. Perfect. And that's what I wanted, right? Where alpha and gamma are real, correct, and beta may be non-real. Beta is non-real. Okay, cool. Right, question 2. Much preferred that one to question 1. So let's keep it moving. Try and make up some of this time and get on to question 3. Consider the curve defined parametrically by these equations. Right, so this is a new one. Parametric equations. X equals 2t minus 3t cubed, and y is t e to the t. Okay. Find the coordinates of any stationary points and determine their nature. Yay. Right, so what we're going to do here is classic parameterized curve equation. So we say dy by dx is dy by dt on the top divided by dx by dt. So that's simply dy by dt is product rule. So e to the t plus t e to the t divided by dx by dt, which is 2 minus 6t squared. So stationary points, stationary when dy by dx is 0, which is when e to the t times 1 plus t is 0. You need the numerator to be 0, so i.e. t is minus 1. Okay, so t is minus 1, so that tells me that x at t equals minus 1 is minus 2, minus 3 times minus 1, so that's just minus 2 plus 3, which is 1. 3 minus, brain's lost it. And y at t equals minus 1, well, that's just minus e to the minus 1. Okay, so that's the coordinate of the stationary point, or the coordinates. Now it says determine their nature. So I could work out a second derivative and check if it was positive or negative for getting a minimum or maximum. But is there a smarter way? That's the question I want to work out. It's not that bad to do the second derivatives, is it? Okay, well, I say that. It maybe is that bad to do the second derivatives. Can I be smarter about this? So I probably can. Let's see what happens. All right, I'm going to do a sneaky thing. So we're going to consider t equals minus 1 plus a small amount. And I'm going to look at if the function is larger or smaller. And that will tell me whether it's a max or a min. That's my idea. So I really don't want to calculate second derivatives. So that's what you should do, but it's going to be a mess because of this. I'm going to have to do like implicit differentiation, and I don't want to do that. So we'll try this, see if it works. So what I'm saying is I'm going to move a little bit away from minus 1. And if I see the function is increasing away from that, it's a minimum. Or if I see the function is decreasing, it's a maximum. That's my idea. So x at that point, right. So I can say that x at epsilon minus 1 is equal to 2 lots of epsilon minus 1 minus 3 lots of epsilon minus 1 cubed. Right, so that's going to be 2 epsilon minus 2 minus 3 lots of, so this is going to be epsilon cubed minus 3, not e, 3 epsilon minus 3 epsilon squared, sorry. Is it a minus? I can't actually remember. Epsilon minus 1 expanded out. I'm going to have to quickly do this, aren't I? So epsilon minus 1 times epsilon squared minus 2 epsilon plus 1. So yeah, epsilon cubed minus 2 epsilon squared. So minus 3 epsilon squared, yes. Yeah, but then you're going to get plus an epsilon plus another 2. So plus 3 epsilon. Sign alternates, yeah. And then minus 1 at the end, yes. Okay, so that's going to now be, so the minus 2 and the plus 3, so it still gives you your 1, and then you've got a plus 2 epsilon, minus 3 epsilon squared, plus epsilon cubed even, plus 9 epsilon squared, minus 9 epsilon. Right? Yes. That looks correct. So we can ignore epsilon squared and cubed because they're tiny. So really, it's 1. So this is looking like 1 minus 7 epsilon, which is smaller than 1. So moving a little bit away from this point, the function is less. So I think it's therefore a maximum. Purely based on moving a little bit away from that point, x is smaller than it was. But I need to know about y, wouldn't I? Actually, wait. I'm not going to conclude maximum yet. Let's just check y. Okay. Yeah, so we're a little bit less than 1, and before we were at 1. Okay, so we've moved a little bit to the left. Okay, right, so i.e. moved left. Okay, fine. Sorry, I don't think I can conclude yet that it's a max. Let's see what happens with y. So y, so we moved a little bit left away from 1, where the previous turning point, or where the turning point is. So now y at this point, epsilon minus 1 is, what's the coordinates of it? T times e to the t. So it's epsilon minus 1 times e to the epsilon minus 1. Okay, so is this larger or smaller than it was? Interesting. Huh. Not that easy to work out. Right, well, it's approximately, let's think about this. It looks like epsilon times e, e to the epsilon, which is tiny, divided by e, right? And then it's minus e to the epsilon over e. Okay, and before it was just, before we had minus 1 over e. Okay, so e to the epsilon is a little bit bigger than 1. Right, so this is larger. So this is greater than. So it's smaller than it, isn't it? So it's negative. So this is more negative, right? So this is more negative. But then we've got a positive term, which is on the order of epsilon. So that's kind of tiny. So I think it's going to be, how much more negative? All right. It's turning into more work than I thought it would, but I think it'll still work. Because I can say that this is approximately epsilon times e to the epsilon over e minus, now we can expand this. So this is 1 over e times 1 plus epsilon squared over 2 plus ... So using the exponential power series, again, way more advanced, but should have just done those second derivatives is what I'm now thinking, but here we are. So this is then equals, we've got 1 over e, we've got epsilon e to the epsilon minus 1 minus epsilon squared over 2 minus ... So this is larger. I don't know if it's larger or not, is it? So if I expand this as well, so I can expand as, it's going to be epsilon times 1 plus epsilon squared over 2 plus ... Right. So I think this whole thing is then approximately 1 over e times epsilon plus epsilon squared plus some other stuff, minus 1 minus epsilon squared over 2 minus some other stuff. So at leading order, this is approximately minus 1 over e, and then we've got plus epsilon minus epsilon, so those two cancel, but then we've got a plus an epsilon squared minus an epsilon squared over 2, so plus an epsilon squared over 2 lots of 1 over e, and then plus some other stuff. So it's a little bit bigger, i.e. a little bigger, so it must be a minimum. Because we've changed x a little bit, we've shifted left a little bit, and y has gotten bigger. So it must be a minimum. Minimum. All right, and that's going to be my answer. Done through a completely unconventional method, but I think that is going to be correct. So let's talk about baseball in part B. So this question looks pretty fun. A baseball diamond is a square with side length 27.4. So I'm going to draw it as a square because I don't think it's actually going to matter. Just kind of rotate the whole thing. So we got this. Let's take this as home. This can be first, second, and third. Right, cool. And we got the distance. A player runs from first base to second base at a particular rate. Okay, so we're moving this way, right? And we know that v, the speed, is 5 meters per second. Okay. At what rate is the player's distance from third base changing when the player is 10 meters from first base? Okay, so we are 10 meters across. Okay. Sure. And then we know the distance. Right, so that's why it's drawing me the triangle. So we're going to call, I don't think I need the thetas here, but we've got theta 1 and theta 2. And we're calling this distance, we're not calling it anything, all right, let's call it L. So we can work this out, can't we? Yeah. So we know that this is 27.4. This is, let's keep it general and call this 27.4 minus x, where x is the distance traveled. X is going to be 10, but let's just keep it general because then I can use Pythagoras. So I know that the distance squared is equal to 27.4 squared plus 27.4 minus x squared. So from Pythagoras, we have this equation for the distance squared. And then we're interested in how is the distance changing with time. So if we differentiate with respect to t, then we'll get a dx by dt term, but we know the speed, which is v. So I think this is how it's going to work. So if we differentiate implicitly, we're going to get 2L times dl by dt. I could, of course, square root, but I'm just, right, it's going to kind of work out the same way. So let's just try and make it a bit easier this way, I think. So 2L times dl by dt, because I'm differentiating with respect to time, yep, that's a chain rule, is then equal to, the constant disappears, and then we get, we bring the 2 down, and we get 27.4 minus x to the power 1, but then by the chain rule, we get a minus dx by dt in there as well. Okay. So I think that's going to be my formula for the change, yes. But now what do we know? We need to use x equals 10. So when x equals 10, which is what we've been asked to work out, we know dx by dt is a fixed speed, which is 5. And we know the distance itself, fun, is the square root of 27.4 squared plus 17.4 squared. Right, so that's L when we square root that. We know X, we know that, so we can just sub everything in basically. So I think we're going to get 2 lots of this square root, 27.4 squared plus 17.4 squared. So that thing times the change that we want, dl by dt, at x equals 10, is going to be equal to 2 lots of 17.4 minus 2 lots. So minus, I'm just going to leave it in terms of numbers, 2 lots of 17.4 and then times 5, because that's the speed. Right, so there's a load of numbers there. You would just obviously divide through by those numbers and get an answer. So it's going to be decreasing, which I agree with. It's going to be like what, 150 divided by whatever that is, 75, and then that's like 7. It's going to be like, oh, I don't even know. Yeah, I literally have no clue. But anyway, it's going to be some number. I'm not sure exactly what it'll be, but like something smaller than 5 is what it should be. But I think that's going to give us the answer. I don't have a calculator, so that'll have to do. Now, part 2 is asking me about angles. So, at what rate are angles theta 1 and theta 2 changing as the player slides into second base at a rate of 5 meters per second? So I think here we need to try and do another bit of implicit differentiation. So in the first question, we were looking at getting an equation for the distance, because that was what we needed to get dl by dt, the rate of change of the distance. So now we want the rate of change of the angles. So we can bring the angle in using trigonometry. So now the question is, do we want sine, cos, tan? Normally you use tan when you're talking about angles. And given we don't know L, and L's complicated, right? That's like square root Pythagoras stuff. I think we're going to want to use tan. So let's try that. So let's say tan of theta 1, for example, is equal to opposite over adjacent. So opposite is 27.4 minus x, isn't it? That's the distance, which is changing, obviously, as x changes. And then the adjacent is 27.4. So we want to now differentiate this, don't we? We want to introduce a rate of change of the angle. So if we differentiate implicitly again, then we can say derivative of tan is sec squared. So we're going to get sec squared theta 1 times d theta 1 by dt is equal to, so that was 1, which now disappears, minus, so it's minus 1 over 27.4 times dx by dt. Right? Yes. And we know that, don't we? We know dx by dt. So, so what can we say here? So that tells us that, yes, dx by dt is constant. So I can say that d theta 1 by dt is equal to minus 5 over 27.4 times 1 over sec squared of theta 1. So we have an equation. When are we trying to work this out? At what rate are the angles changing as the player slides into second base? So it's literally as we come in, and as we come in, theta 1 is decreasing all the time and tending to 0. So we want this. We want d theta 1 by dt at theta 1 equals 0. Yes. So that's just going to be minus 5 over 27.4 times 1 over sec squared, but 1 over sec squared is cos squared, isn't it? So instead of doing it as a 1 over, it's just cos squared of 0. Okay, great, which is 1. Yay! I was worried I was going to be dividing by 0. So this is now cos squared of 1. Sorry, cos squared of 0, which is just 1. So I think the answer is just minus 5 over 27.4. And let's say that's going to be in radians per second. So that is d theta 1 by dt at theta 1 equals 0. So as we slide into the base. So if theta 1 is decreasing at that rate, then theta 2 must be increasing at the same rate because it's always a right-angled triangle. Okay, so since right-angled triangle, so the total angle has to be always theta 1 plus theta 2 has to be 90 degrees. Since right-angled, theta 1 plus theta 2 has to always be pi over 2. So therefore, the rate of change of theta 2 at that point must be the exact same. At the point when theta 1 is 0 must be plus that. So 5 over 27.4 radians per second. That's just to make sure that everything balances. And that's it. All right. Part C. So, well, this is different. A gate manufacturer uses steel to produce 5 gates per day. Right. I have no idea where this is going, but 5 gates per day. Okay, note some of this down. Delivery for any amount of steel ordered is $5,000. Okay, so delivery is a fixed price of $5,000. All right, seems steep even for New Zealand dollars. If the manufacturer orders a large quantity of steel, this will reduce delivery cost per unit. Yeah, get that. But it will increase storage costs. And it's $10 per day to store 1 unit. God. Very economics. $10 per day per unit of steel. Okay. So the idea is, I can kind of see where this is going. I haven't read the question yet, but it's going to be like, how many do you get delivered to maximize, to minimize cost? So you want to maximize the discount of getting loads delivered at once, but you also want to minimize storage costs. So you don't want to get too much delivered at once. There's going to be a sweet spot. Right. And it's $10 per day to store it. Yeah, amazing. A unit amount of steel to produce a gate. Great. How often should the manufacturer order steel, and how much should they order each time to minimize the average daily cost of delivery and storage for each production cycle? So we're going to start by defining some variables. So what have we got to work out? How often should they order steel, and how much should they order each time? Okay, so let's suppose order every X days, right? And there's no mention of like weekends or work days or anything. No, 5 gates per day. So we're ordering every X days, and each day can produce 5 gates. So we need to order, I guess, at least 5. Oh, so minimum, right, so minimum order of 5x to cover production between deliveries. Okay. Right, so if I'm ordering every like 10 days, I better order 50 units because otherwise I won't have enough steel to produce, right? So it's definitely going to be at least 5x. Okay, fine. Now, how do I think about this? So what's the storage cost? Right, so let's think about the cost function here. So the cost of x is the delivery, which is 5,000, that's fixed, plus storage. Now I have no idea what storage cost is, so let's think about this. So storage is $10 per day per unit of steel. So the storage cost is definitely $10 per day, and we're ordering every X days. So that's 10 times X. But now how many units of steel will be left? So if we ordered 5X, then we would have how many days? So on the first day, we would have 5 lots of, we would have 5x minus 5 on the first day. Then we would have 5x minus 10. Then we would have 5x minus 15. And we would keep doing that until we got all the way down to plus 5, and then we'd be done. Right, I think. So I'm just thinking there, we're using 5 each day. So like you'll get a delivery, 5 are used that day, so then there's 5x minus 5 after that. So how many is that? Then can I add that up? So let's think about that. So this here is the, this is like the cost per day in a way of storing the stuff. So that's going to be, what have we got? We've got 5x times how many times? Times, it's 5x times 1 plus, wait, no, not quite. because then it would be 5x minus 5. It's 5 lots of, okay, so this is like a sum. I think it's like a Gauss sum where you can match the two up. So I think what we've got here, he says, is you've got 5 lots of x minus 1 plus x minus 2, yeah, plus dot 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 plus 1. Right, and that's a Gauss sum. So that's 5 lots of. The sum to n minus 1 is, sum to n is n times n plus 1. So it's n times n plus 1 over 2. Right. Okay, cool. So that's the amount of stuff that we're storing times 10x. So I think I've got a cost function. And a neat little use there of the Gaussian sum. So I think the cost is actually going to be 5,000 plus 10x times 5x over 2 times x minus 1. All right, so that's going to be, let's just simplify that a little bit. 5,000 plus 50 plus 25 times x squared times x minus 1. Okay. So I think this is my cost function, and I am trying to minimize the cost function with respect to x, aren't I? Yes, all right, so we want to minimize the cost function. So it means differentiating, setting x to 0. So we want to solve c prime of x equals 0. Right, and it's clearly going to be a minimum because as x increases, the cost just goes up and up and up and up. So we're going to have a minimum turning point in the middle there. So c prime of x, differentiating with respect to x, then is, oh god, my product rule it, it's fine. Fine, I'll just expand it out. Don't overcomplicate things, Tom. 25x cubed minus 25x squared. That's what I've got. So if I differentiate that, I'm just simply going to get 75x squared minus 50x. We set that to 0, so I can cancel because we don't want x being 0, obviously. So that's 75x minus 50 is 0. So that's x equals 50 over 75, which is not a whole number. So that seems to be suggesting 2/3, which obviously isn't the answer. So what have I done wrong? All right, we've done something wrong here. Let's reread the question. How often should the manufacturer order steel, and how much should they order each time? So that's, well, I'll figure that one out later. To minimize the average daily cost of delivery. Right, so I've worked out the total cost per cycle. So I need the average daily cost. Minimize the average daily cost of delivery and storage for each production cycle. So I think actually what I want to do is divide by x. So I think this should have an x here, and then this is over x. Because then it's the cost per day, because x is the number of days, right? In a cycle. Yes. Okay. Right, so I think I need to go back then. Let's erase that. So it's the same idea. I'm going to minimize it exactly as I've done. But I'm just going to get a slightly different function because there's going to be these negative powers of x floating around. So let's do that. All right, so I think it's that, which then simplifies into 5,000 over x plus, it's still 25, but now it's going to be x squared minus 25x. Okay, cool. So let's try that instead. So c prime of x equals 0, so I think that means that c prime of x is minus 5,000 over x squared plus 50x, right, because now the 5,000 is relevant. Okay, I get it. Because before the 5,000 disappeared, but that's not right, because it's sort of a per day average when you work it out. Right, cool. Plus 50x minus 25. Okay. So, what's the solution to this? So I want this to be 0. So I need minus 5,000 plus 50x cubed minus 25x squared to be 0. So it's the solution to that cubic. Marvelous. I have a feeling I shouldn't end up with a cubic. All right, well, what's gone wrong here? This could be wrong. My intuition tells me this isn't right. It just seems too tricky. So what have I done wrong? The average daily cost of delivery and storage. The average daily cost. So I've got too many x's. So maybe it's up here. So if this is the average, well, this is the exact cost, isn't it? Right, because it's just, how many are there? So what's the average cost? It's 10x times the average amount of them. Oh, so if we start, okay, I see. So if we start with, might have overcomplicated it perhaps. So if we start with 5x and we end with 0 after x days, the average, right, the average is 5 over 2. 5x over 2. So that would actually simplify this. Okay, so if I use that one instead, right, so I don't know if, I have no clue if this is going to be right, but I just don't think it's a cubic. So if I use this average one instead, then basically I'm sacking off that. So that term's not there. Everything else is fine. Wait, except that's just x now, isn't it? Okay. So that's now just x. That term's disappeared. And so this derivative has the plus 25. So that's gone, it's just plus 25. Right, okay. So this is a bit simpler. So I think, okay, so the alternative, where we do the average amount stored rather than the Gaussian sum, the average there is going to give us, what is it going to give us? It's going to give us minus 5,000 over x squared, plus 25 is 0. So in other words, 25x squared is 5,000. So x squared is, oh God, 200? 200. Now that looks a bit simpler. So x is like 14, maybe? Okay. 14-ish. 14 and a bit, right? 14 squared is 196. So approximately 14, that would be the nearest integer. Okay. But if we're ordering every 14 days, then we need to order 70. Right. And then we would be ordering order 70. Is that the answer? How often should they order steel and how much should they order? All right, I think it's 70. I could also try and solve the cubic. Don't want to. Because I don't know, would 70 work in the, let's see, would 70 work in the cubic? Now I have an idea of what the solution might be. So 70 cubed, God, is like 50 times 70 is like 3,500 times another 50, wow. Okay. Oh God, that's a big number. Minus 5,000 and minus that. Okay, so this would be like minus 5,000. 1,000 plus 50 lots of 3,500, and then like minus 25 lots of like 50. So it's going to be super positive. Okay. Not sure. All right, sod it. We're going 70. 70 it is. And that's it, because I need to get on with question 4. Right, find the area of the region enclosed by these two parabolas. Okay, this is more like it. Okay, I'm not even going to draw this because I know what's happening. We've got 6x minus x squared is on top. So I want the integral of the one on the top of 6x minus x squared minus the one on the bottom, which is x squared minus 2x. Okay, so I just need to integrate that between a and b, where a and b are the intersection points, are points of intersection. So let's work out those, and then let's just do the integration. So, right, so the intersection points occur when 6x minus x squared equals x squared minus 2x. So that is, moving it to the right, 2x squared minus 8x must be 0. Yes. So that tells me that x squared minus 4x must be 0. So that's x is 0 and x is 4. Okay, so a equals 0, b equals 4. We knew 0 from the picture, we didn't know 4 though. So therefore the area is simply the integral from 0 to 4 of 6x plus another, so that's 8x, doing that, and then minus x squared minus 2x squared dx. Right, so do the integral, so that's going to now be x squared, and then a 4, because we increase the power, divide by the new power, minus 2/3 x cubed between 0 and 4. So we're just going to get the answer when it's 4, so that's 4 times 16 minus 2/3 of 4 cubed, which is 64. I've written 2/8 for some reason. Told you I was running out of steam. 2/3 of 64. So that's 4 lots of 16, which is 64 times 1 minus 2/3, so 64 over 3. 3 is the answer. He says, all right, B, keep it moving. See if we can whiz through this one, that'd be nice. Evaluate the definite integral, the integral from 1 to 4 dx over x minus 2. So 1 over x minus 2 to the 2/3 dx. Right, so I probably would have just integrated, but they've given me a hint here. Consider using limits. So I'm guessing this is to do with the fact that this function is not defined at x equals 2. Okay, so function undefined at x equals 2. So I think what we need to do is split it up into 1 to 2 and 2 to 4. Try and do it that way. So therefore we consider the integral from 1 to 2 of 1 over this to 2/3 dx plus the integral from 2 to 4 of 1 over x minus 2 to the 2/3 dx. Because the function itself isn't defined there, but when we integrate it, we're going to get the whole thing to the third, and so we're actually going to get zeros at those at the points when x is 2. So the integrated value is going to be okay. It's not going to be infinite. So I think that means it's all right. We'll see. But I think this is what it's hinting that I should do, right? So it's kind of saying I want to take the limit here as we go to 2 minus, and then the limit here as we go to 2 plus, is really formally what we're doing. But I'm just going to do it without the limits, because it's fine. I'm just going to get the answer at this point. Right, so I'm just going to integrate the function. So that integrates to give me x minus 2 to the power of a third. And then you would bring the power down. So I must have a 3 outside the front. Great, so it's just that at 1 and 2, and then plus the same thing at the same points 2 and 4. So it's then going to be, so I should really write, fine, I'll write the minuses and the plus, otherwise there's not really much point in doing what I'm doing. So I'm going to get 3 lots of x, well not x is it, it's 2 minus 2, minus 2 to the 1/3, minus 3 lots of 1 minus 2 to the 1/3, and then plus 3 lots of 2 plus minus 2 to the 1/3, minus 3 lots of 4 minus 2 to the 1/3. So then those two are basically going to cancel each other out because they're both going to be 0. In that limiting process, they're both going to be 0. And so what we're just going to end up with then is minus 3 times the cube root of minus 1, which is minus 1, minus 3 times the cube root of 2. Okay, so I think the answer is 3 lots of 1 minus the cube root of 2. But, hang on a minute. Slight mistake. I just realized that's negative. I was like, that makes no sense. So I made a slight error there because I was meant to subtract. I did the limits the wrong way around on that second one. So they're going to be, right, yeah, I get it now. So that's a minus and that's a plus. So that's a plus. So that's now a plus. Yes. Because the point was these two cancel out when you take the limit in the limit as we actually tend towards 2. So yeah, so they're going to cancel out. Okay, great. So I think the answer is 3 times 1 plus the cube root of 2. And I'm going to move on to part C. Oh, all right. When a curve is defined parametrically by these equations, we define the length of the curve using this formula. Great. So L is equal to T1 to T2 times the square root of dx by dt squared plus dy by dt squared. Yep, happy with that. I like how it's just giving me lots of formulas that, like, normally I would maybe derive, or, you know, well, we would derive at university, I should say. But, you know, here it's like, here is a nice formula. Here is a nice limit you might want to use as a hint. It's good. All right, but it's nice. These are quite advanced topics, so I like it. Okay, an asteroid is the curve produced by this. Right, great. So we have a parameterization, and I'm going to do the integral, right? Great. So parameterization then is cos cubed of t, y equals sine cubed of t. And by symmetry, I can make this a lot easier for myself. I'm going to go between, so I can just say L is actually just going to be 4 lots of the integral from 0 to pi by 2. Because I'm working out the perimeter, it's very symmetric, right? So the shape is, I should have probably drawn the thing. Shape is this, right? So you've got the same value in each quadrant. So I'm just going to work it out in the first one. And then I don't have to worry as much about signs of, you know, sine and cos, because that's annoying. So work it out in the first quadrant and just multiply by 4. Keep it simple. Right, but I do need to know what these derivatives are. So let's work them out. So dx by dt is just cos cubed, gives me 3 times cos squared t. Derivative of cos is minus sine of t. And dy by dt is then just 3 sine squared. Derivative of sine is cos of t. So putting them in, what have we got? So the whole thing's squared. Wow. So that's going to be a 9 times a cos 4 times a sine squared plus a 9 times a sine 4 times a cos squared. Right, so this is going to simplify quite nicely, isn't it? So L is equal to 4 lots of integral 0 pi by 2. Right, so we can take out the root of 9 and get that. And then what we've got in here is we've got a cos squared times a sine squared. Should really add the t's in. And then the first one is a cos squared. That's the factor. And the second one is a sine squared. But of course, cos squared plus sine... I knew where this question was going as soon as I started plugging these things in. Cos squared plus sine squared is 1, right? So that disappears, and then we can square root. So we can say that L is 4 lots of the integral from 0 to pi by 2. Now, this is where my little trick of saying it's 4 times the first quadrant is going to really help. Because in that first quadrant, cos is always positive between 0 and 90, and sine is always positive. So the square root is always positive. Otherwise, you might have to worry about changing signs in each of those 4 regions. But again, perimeter is just 4 times the perimeter in that first bit, because it's a distance and the symmetry tells you it's the same in each one. So we just got 4 times 3, to take the 3 outside, so that's 12, and then the square root of that. So it's literally just cos t sine t. And that's all I have to do is integrate that, which is awesome, because that I know is just, so I can write that as 6 lots of cos t sine t is now 2 cos t sine t has come from sine of 2t. From the double angle formula, that I can integrate, that's just 6 times sine of 2t has come from cos. So if you differentiate cos, you get minus sine. So let's just put a minus on that. And we would bring out the 2, so we would have to divide through by that 2 between pi by 2 and 0. So I believe the answer there is going to be minus 3 cos of pi, which is minus 1, minus minus 3 times cos of 0, which is 1. So I think I make that 3 plus 3 is 6. So I think the perimeter of the asteroid is 6, which thankfully brings me on to the last question of the last question. Part D, question 4. It's been a long one. All right, D. A function is defined implicitly by the following formula. Again, sort back. Following formula. Right, let's finish this off with a bang, eh? F of x is, okay, so already I'm just going to square both sides because I'm not writing the square root out. So the integral from 0 to x of f of t squared plus f prime of t squared, right, dt plus 2023. The classic, use the current year in one of the weird functions question. All right, find an explicit expression for f in its simplest form. Hint, if f is continuous on an interval, then the derivative gives you the function. Yes. So basically it's saying, please differentiate. Okay, so differentiating, which is suggested by the hint. So basically we're using here the fundamental theorem of calculus. So we're going to get, again, we've got to be implicit, lots of implicit differentiation in this exam. 2 lots of f of x times f prime of x is equal to, using the hint, the derivative is just the function evaluated, so f of x squared plus f prime of x squared, and then the 2023 disappears. Right. So how do I solve this? That's a good question. Okay. So if I kind of rearrange this a little bit, we can say I've got f of x squared minus, it's a square, isn't it? Minus 2f times f prime, and then plus f prime squared. Right, so it's actually just a square. So it's f minus f prime squared equals 0. So now we get something we can solve. This is neat. This is neat. Good one to end on. So we're saying that f of x equals df by dx. Now, which function does that? Well, that's an exponential, isn't it? So f equals e to the x. And there could be a constant in front of it. Right, a times e to the x. And just to make that a bit more formal, don't know if I'm allowed to just quote that. What basically you're doing here is you're saying the integral dx equals the integral of 1 over, pardon me, f df. So that says that x plus c is equal to log of f. So then you exponentiate both sides, and that tells you that a times e to the x equals f. Okay, so f is an exponential function. So now let's put it back into our expression. Let's call this star. So sub into star, because what did I have to find? Explicit expression for f. So I need to solve for c. So I need the constant, don't I? Right. So I sub into star. What do we get? We get a squared e to the 2x is the integral from 0 to x of f squared, so a squared e to the 2x, plus the derivative of it, which is the same thing. Oh, so let's just put a 2 there, because the derivative is equal to the function, which is nice, dt, plus 2023. Right. So when x is 0, so I can actually, I don't need to do the integral, I don't think. So when x is 0, this actually tells me then that a squared equals 2023. So i.e. f of x is in fact just the square root of 2023 times e to the x. And that's it. I'm calling it. That's the answer. That's it in its simplest form. It's the end of the exam. We've done it. We've got there. So as usual, I'm going to take a little break. Maybe go and stretch this back out, have a drink. And in just a moment, I'll be back to give you my thoughts. And we'll get to the important part. We'll do the marking. Right, we're back. Raring to go and see how I've done. Got the mark scheme in front of me. Going to look through my answers, see how I score them. Again, I'll do this pretty quickly as I do in the past. I don't want to focus too much on the details. If I've got the right answer, I'm going to give myself the marks and we're going to move on and talk about the ones where I perhaps didn't get the right answer. But before we do that, I just want to sort of evaluate my thoughts a little bit, or state my thoughts on the exam. It was kind of hard. There was a lot of stuff in there. The geometry questions I didn't really like. We'll see how I got on with those, but I'm not so confident about those. There was the one about the steel that was like the economics problem. I have no idea how I've done on that one, like literally no clue, because I kind of couldn't decide what the best method was. And even some of the calculus ones, like, I'm just not sure. I feel less confident about this ahead of marking. So I will reserve full judgment until I finish marking. But I think that was actually quite tough, to be honest. I think 17, 18-year-old taking that exam would find that pretty tough. But let's get to the marking, and then I'll give you a full rundown, a full opinion, and a full ranking of where it sits compared to all of the other exams I've done from around the world. So, question 1. What have we got? Q has coordinates -6, 8. Yep, I said that. R is 10, 0. Yes, I said that. So y is -1/2 x plus 5. Oh! So I have 1/2 x minus 5. So I seem to have got a positive gradient. It's a negative gradient. Good start. Good start. So it's minus that. Minus and a plus. So bad start. And I don't know how many marks I've lost. Interesting. So I'm out by a negative sign, because the gradient is of course negative based on the graph. That was very silly of me. Very silly of me there not to spot that. All right, well, good start. So we dropped some marks there. Okay, right, oh God. Part 2, this idea about prove that the line RT is parallel to the line PQ no matter where they intersect. Okay, so the answer does mention symmetry. It says they have a common axis of symmetry of y equals minus x. And I did talk about that, yes. And so therefore they're parallel. All right, so I probably did more than I needed to according to the mark scheme, so that's good. Logs, okay, solve the system. Let's just look at the answers. X is 2 to the 4/3. Yes, good. And y is plus or minus 5 to the minus 11 over 6. Okay, so I am missing the plus or minus. I just have the plus root. So maybe have forgotten a square root there. Don't remember square rooting, but nonetheless, all right, fine. I will trust the mark scheme on that one. Fine, I've apparently forgot a plus or minus. Okay, part C, the parabola. Oh God, so it says here k is b squared over a. Yes, eventually got that one. Work out some stuff. The gradient is minus a over b. Yes, I did do that, good. And then work our way through. I'm pretty sure I got this because it made it work after I spotted my mistake. Yeah, they've done something very similar. Okay, so that one's all right. So if this is out of 8, and I guess I've made 2 errors. I did sensible maths. I missed the minus sign on the first one, so I'm definitely losing a mark. The other one, I forgot the plus or minus on the root. So probably, again, deserve to lose a mark. So I think that's going to be 6 out of 8. I think. Which is a terrible start, because there aren't many marks available in this exam. But I think that's 6 out of 8. Just dropped a couple there for some minus sign errors. Easy to do. Easy to do. Okay. So let's then move on to number 2, shall we? Yes. So question 2 now. Okay. So first one is 2 over root 13. I think I got that, didn't I? Yes. Okay. Good. Part B. Work out z bar to the 4. It says it's minus a half minus root 3 over 2i. Yes. Good. Part C, part 1, e to the minus pi. Yep, brilliant. And then this weird rectangular form thing. I pi plus log 25 plus e to the minus pi by 2. Amazing. Okay, so good job I did make that logarithm, use the complex logarithm there. Okay, and then the last one was the circle equation. So alpha is a, gamma is d, and beta is b over 2 plus c over 2i. b over 2, they did not rationalize their denominator, but we've got the answer. Okay, so 2 was better. 2 was better, that's 8 out of 8, thank God. Right, 3. Parametric curve. Okay, oh, this is where I didn't want to differentiate, wasn't it? Okay, find the coordinates of stationary points. So coordinate is 1 and minus 1 over e. Excellent. And the curve is a minimum. I did say minimum, right? We did. We took our time to get there, but I did say minimum. Good. Okay, baseball. This was a weird question, very weird question. Okay, so part 1. Oh God, I didn't do this in a calculator, did I? Okay, so it reckons the answer is 2 times L, where L is that. Yes. So I'm just looking at their answer where they haven't actually, well, they eventually plug it into a calculator, but I don't have one. But that's correct. You divide by that, and then you've got 2, a minus, a 5, and a 17.4. Okay, so that will give me the answer when I plug it into a calculator. And then d theta 1 by dt, wasn't sure about this one, is minus 5 over 27.4. Yes. Didn't think I would have got that. And then the other one's going to be plus. Perfect. Good. Right. Gate manufacturer. There's no way I've got this correct. Let's see. Okay, so it wants me to do the average amount in storage between deliveries is 5x over 2. So it did, okay. I'm still not convinced by this because I think my original method was more accurate. But apparently 5x over 2 is what they wanted. So then C is 5,000 over x plus 25x. Yes. Somehow. Did I differentiate correctly? So I think we should receive a delivery every root 200, which is about 14 days, and order 70 units of steel. Whew, did not expect that. Will definitely take it, but did not expect that. Okay, right. So wow, was that extremely unconfident with question 3, and he somehow pulled an 8 out of 8 out the bag. And then 4 I actually liked. So 4 was actual calculus. So I think, fingers crossed, we're going to be all right here. 64 over 3, amazing. B, this is this weird deal with the limits thing. 3 plus 3 cube root of 2. Boom, nailed it. Asteroid is 6. I think I got 6. Yes. And then the final one. Ooh, this one felt a bit too oh no. Okay. Felt like it kind of fell out a little bit too easy in the end, but no. Root 2023 times e to the x. So that's another 8. So that means a final mark there, 30 out of 32. So basically, the ones I was not confident on, question 3, baseball and gates, somehow got them, and the ones I was more confident on, question 1, made some silly errors. So yeah, so I got the gradient wrong. I was so silly. It's clearly a negative gradient. And apparently I missed a plus or minus on the log question. There was a y squared in there, so maybe I've just forgotten. It could be either. But very pleased with 30 out of 32. Very pleased. So where does New Zealand rank on my list of exams from around the world? I mean, I'm pretty pleased with 30 out of 32. So I think that the fact that I am very pleased with that, I think tells me that was quite tough. So I think, as I mentioned before the marking, I think that the baseball question was weird. I kind of guessed my way through that. The steel one, I have no idea how I got that correct. Like that was, I felt like my answer was nonsense, and yet somehow was the answer they wanted. I still think it should have been the cubic and the Gaussian sum, but it was that word average, and I was like, Anyway, so I'm not really convinced that I fully grasped those questions, but somehow got those answers. And I did make some mistakes, but they were just a little bit silly with minus signs. So I think overall the concepts were okay. I think like question 4, for example, with like the integrals and the parameterizations and the sort of perimeter and arc length type stuff, that's probably going to be really hard for a high school student. But I found question 4 the easiest of all of them because it was like, oh, it's just like first year university calculus. It's what I teach to my first years. I'm used to this. So I think that helped me out towards the end. Again, no idea how I did well on question 3. Question 2, what was that one? That was like, 1, obviously we know I didn't quite, made some silly mistakes on. But question 2, what was that one? That was, the trig and the complex numbers. That was also fine, actually. So it was 1 and 3. So basically, I found questions 1 and questions 3 pretty tough. 1 was just some awkward geometry, especially that last one, trying to show with the parabola and the value was k. That was messy. And I was lucky there because I spotted my error, or my error didn't come back to haunt me because I got the wrong k value because I made a silly mistake. Apparently, today's the day I'm making silly mistakes. We all do it. We're all human, right? Even mathematicians. So I think I was lucky with spotting that in question 1. I made a few other errors. 2 complex numbers, absolutely, totally, no problem with that. 4 calculus, no problem with that. 3 felt like weird questions, right? The baseball one and the kind of steel one, kind of like applications of calculus, but again, I'm not really sure how I got those correct because I felt like I was fudging a lot of it. So I think it's going to be, I'm sort of like thinking somewhere around like the arbiter, right? So I remember the IB, right? The IB, was really long. I feel like the IB was just like a slog and took me like all of the time because it was like never ending. So this one didn't quite feel never ending, but it did feel like it had harder topics. And I remember the Arbiter had like that really awful question about like centers of spheres and stuff, which I think I was screwed over by a mistranslation, and I'm not bitter or anything, but I keep mentioning it. But that was quite a hard geometry question as well. So I'm going to put it somewhere around like Arbiter and IB. Maybe let's say harder than the Arbiter, easier than the IB. I think I'm going to put it there. But I do imagine questions 2 and 4, which I thought were the easiest, would probably be quite hard for a high school student. So based on purely my experience, I'm putting it between Arbiter and IB. But I think for an actual high school student, it probably would rank a bit higher. And judging the fact that it has a name of like scholarship calculus, I'm assuming this is like a special exam maybe that's taken by quite advanced students. Anyone who has taken this, anyone from New Zealand who understands how this works, please let me know in the comments like what that term scholarship means. Is this like the best of the best, as it were, or is this even part of a university application process? I really have no clue, right? I get sent these exams. Thank you for sending them to me. Please send me more. But I get sent these exams. I'm like, cool, let's try New Zealand today. Is kind of how it goes. So please tell me more about what the scholarship thing means. But from my perspective, it's going to sit around like Arbiter, IB kind of level on that tier list. Right. So that brings us to the end. I have taken the 2023 New Zealand Calculus Scholarship exam. And I have scored 30 out of 32, which according to the mark scheme makes me an outstanding scholar. You needed to get at least 29 for that. So I was cutting it fine, but I did get the outstanding scholarship. You also needed to score at least 17, so at least half marks to score a scholarship, whatever that means. I don't know whether this is related to scholarships or not. Again, please let me know. But officially, I am an outstanding scholar. So thank you as always for sending me the exams. Thank you for watching the video. If you haven't already subscribed and you've got this far, then please do. And then you'll be notified when I do more exams from around the world. I've got 2 or 3 lined up over the next few months, so these will be coming at a faster pace than usual. I have listened to you as the audience. You seem to enjoy these, so I'm going to try my best to keep churning these out. They take a lot of effort. Let me tell you, they take a lot of effort. But thank you for supporting the channel. Thank you for watching. Subscribe, check out Patreon in the description, and otherwise have a great 2025, and I'll see you all soon.